him. Lorenzo has been a pillar, has been extremely influential in distributed systems, consensus protocols, and all of these things which probably we don't know as much as we should. And he graduated in Italy from Bologna. He came to Cornell, got his PhD in '96. Then he went to UT Austin, where he got an endowment professorship. And then he went back to Cornell, to alma mater, to he became a professor there a few years back, right?
Yeah,
and,
4 years back.
Where he is a Tisch University professor of computer science. He got numerous awards. He's IEEE ACM fellow, and he also is the advisor of Natasha Crooks, who accepted our offer, and he will join us soon. And finally, he likes classical music and Italian red motorcycles,
yep.
right?
Yeah, yeah.
Maybe you'll have some pictures on that?
No, I may or may not. May or may not. But the color wouldn't be right, because my red is becoming blue.
Right, okay.
Is that
He
okay?
has very nice pictures on his homepage and so forth. Yeah.
Okay.
So without further ado, please welcome, join me to welcome Lorenzo.
Thank you for having me.
It's student is going to teach you to be part of the faculty. Is informative, or this is one of the honors, like being ACM fellow?
It's probably, I mean, yeah, probably is one of the honors. Wonderful to see you guys. Very happy to be here. So I call this talk the pit and the pendulum, and maybe some of you know what I'm referring to. Are you guys familiar with the story of the pit and the pendulum? Anybody? No? So, yes, it's been a while? Yeah. But you may recall vaguely what this is all about. So it's actually it's a story of Edgar Allan Poe, for those of you who remember Edgar Allan. The story approximately works like this. We are during the Spanish Inquisition, and there is somebody that is accused of some misdeed, and is brought in front of a tribunal, and of the Spanish Inquisition tribunal, and they find him guilty. And so when he hears that he's found guilty, he actually loses conscience. And when he wakes up again, he's in total darkness. He's tied to a table. It's underground, can't see anything. The only thing that he can hear is this swoosh, swoosh, swoosh. And this swoosh, unfortunately, comes from this pendulum. And at the end of the pendulum, the problem is that at the end of the pendulum, there is a blade, and the pendulum is getting closer and closer. By the way, you probably didn't expect me to make a reference to the Spanish Inquisition, but nobody expects. So the reason that I'm presenting you this story is because I actually think that there is an analogy between our friend here. I will get to that. An analogy between this guy and, of all people, database programmers. I'm going to claim that database programmers have also been living with a pendulum that has been swinging over their head, or sometimes inside their head, between two seemingly irreconcilable goals. On the one hand, ease of programming, and on the other hand, performance. And everything started nicely pegged on the side of ease of programming, which with properties like ACID guarantees that you're all familiar with. But then things have started moving, and they've started moving more recently because of some of the work that the systems community has done in all these NoSQL kind of thing, until, going way over the performance side, until people started to realize that it was actually difficult to program in these models, and the pendulum started swinging back again. So let's try to understand, if you don't mind, let's start to understand a little bit more how all this pendulum swinging has come to pass. So as I was saying, in the beginning were these acid guarantees, right, that we are all familiar with. And, let's face it, it's actually very nice to be able to take a bunch of operations, wrap them in what we call a transaction, and as a result of that, have the guarantee that all these operations are going to occur or none of them is going to occur. And it's not going to matter if they have to occur concurrently with a bunch of other transactions. There's correctness is still going to be guaranteed. And furthermore, there is durability that is given to us. Transactions like diamonds are forever. So, so there is no question that transactions are nice. The question that people have been struggling with from the beginning is, can we afford them? And it's actually the database people that have started to weaken the guarantees of ACID. They have started to introduce a bunch of different levels of weaker notion of isolation. And here you see some flavors that have actually started moving the pendulum to the other side until we got, the systems people got into the action. And they started talking about things like an approach that they call BASE, that stands for supposedly basically available, soft state, eventually consistent. It's just a geeky way to say not acid. And the idea of this BASE approach is to say, well, transaction guarantees, very nice. It would be too bad if something were to happen to them. And indeed, they blow up transaction guarantees, and instead they introduce a much weaker, simpler also API based simply on put and get. And actually, the idea is that through this simpler API, you're going to be able to squeeze every ounce of performance in terms of exploiting concurrency until you realize that actually then the enforcement of correctness is then left to the application. And it can, since now you have to start thinking about all the possible interleavings that may occur as you are trying to execute your supposedly very fast code, complexity very quickly gets out of control. And, and the pendulum swings badly on the other side. So then here we are, back to our story. And what I would like to, what I thought would be fun would be to share with you something that we have tried to, what our trajectory, intellectual trajectory has been, trying to see what we could understand in this tension, to try to sort of break the fate of our poor database programmer, okay? And that's really the goal, to share with you more than the results themselves, although I find them interesting, that as they say, it's the journey, not the destination. So I think there is value in the journey as well. So if you start thinking about this problem, what makes it challenging is that the very ingredient that we would want to add to our soup to make it more performant is actually the same ingredient that is going to make it more, that is going to add complexity as well, which is increasing the degree of concurrency that you may have in the system. To give you a sense, let's consider something very simple. Here is a fairly trivial transaction that is doing a transfer between a checking account and a saving account after verifying that there is enough money in the savings account to do the transfer. One way in which I could imagine increasing concurrency here would be to take this transaction, and if I want to increase concurrency, chop it in a couple of transactions so that I separate what's going on with the checking account and what's going on with the saving account. And the good news, if I do something like this, is that while before, if I had multiple transfer operations, they had to be executed sequentially, now I could imagine overlapping some of these two transactions executions. Unfortunately, of course, there are issues with this trivial approach. And the issues become, you probably have already thought about them, the issues become very obvious if I'm adding to the picture another transaction that otherwise would be a fairly innocuous transaction, a transaction that simply tries to compute the balance of my account. And it used to be the case, before I did my chopping, that that balance transaction could only observe the state before the transfer had initiated or after the transfer has completed. But now I have, by chopping, I have made visible an intermediate state here that actually can be observed now by the balance transaction. And as a result, I may actually have my balance transaction compute an incorrect result, right? Very straightforward. So beside the specific of this trivial example, the painful lesson that this trivial example teaches is that that means that if I make any changes in any of my transactions, if I open up any of my transactions, and in so doing, I expose some intermediate state that were invisible before, I have to start thinking about what are the implications for correctness when it comes to having exposed those intermediate states with respect to all other transactions. And that's where you start seeing where complexity becomes an issue. So, yes?
I have a question. So if you had split the part one into parts, I would be evidently be very interested because sequence that would spend the $10.
Correct.
But the way you split sequence that would spend the $10 is just that S, you don't know S is balance, you don't know S is actual balance, you will think S has less than S has. And in some cases, for example, in cryptocurrencies, people are happy to tolerate that situation where for temporary you think S has less than it has, but they don't want to tolerate double spending. So there are situations when it's fine, others when it's not fine.
That could be, but if I'm thinking about a system that is trying to maintain, as you know, database people talk about consistency in a way that is different from how distributed system people talk about. For my understanding is that when I talk about databases, consistency applies, applies to the notion that you would like to make sure that if there are some invariants that hold in your system, your transactions are going to maintain those invariants as they execute. And here, there is an invariant that I was expecting when I was computing, and that is broken. That's what I was trying to say. So I would like to submit to you that the challenge that we are facing seems to be a fairly fundamental challenge then, because in a nutshell, if I want to have better performance, I have to some way expose a larger opportunity for interleavings, but if I expose a larger opportunity for interleavings, then I have to reason about these additional interleavings that become available, and that's the source for complexity. So, so when facing a situation like this, we thought about it for a while and eventually decided to turn to this guy, and not just because he has a nice, beautiful beard, but of course because he's Italian. His name is, and also, by the way, his name is Vilfredo Pareto. That may have also something to do with it. So Pareto, as you know, is known for many things, but one of the things that he's known for is something called the Pareto principle. The Pareto principle says that if you look at a complex system, and if you try to see how the system behaves, it turns out that not all components of the system are equally responsible for the behavior of the system. Pareto had something that he called the 80-20 rule that says that 80% of the causes that you see in a system typically is caused by something like 20% of, 80% of the effects in a system are typically caused by 20% of the possible causes. And in software, we have something that is even more extreme sometimes. We call the 90-10 rule sometimes. And so one of the things we started thinking about was, if I'm thinking about the fact that there is a perception that transactional application sort of push over the performance boundaries of what ACID transactions, the ACID paradigm can provide, the question that we ask ourselves is, does, by chance, the Pareto principle apply also there? So that if you want, sorry, I forgot a clicker. So that, is it the case that indeed not all transactions are created equal? That there are perhaps some transactions that are particularly responsible for pushing on those boundaries, and most transactions are not. And at least in our experience, looking at a bunch of applications and trying to analyze them, we found that to be indeed the case. There is only a handful of transactions typically that are the ones for which the confines of the ACID paradigm seem to be a little tight. Because there are many reasons for this, because many transactions maybe are not run that frequently. Some transactions are inherently lightweight. Again, relatively few are, allow me to call them performance critical transactions. So if we try to then digest this bit of information, and we go back to our picture that I was showing before, in some respect, this picture seems to say something that is even more potentially disturbing. What it says is, remember that I was saying, well, let's try to achieve more concurrency by perhaps increasing interleaving by chopping transactions, say. So what I just said seems to suggest that if I chop transaction, one thing is guaranteed, I get more complexity. But in most cases, I don't get performance. Because most of the cases when I chop transaction, I still am exposing intermediate state and I have to worry about my invariance holding. But in most cases, chopping the transaction, actually, even after I introduce concurrency for transactions that are not performance critical, I'm really not helping the case very much. That's one way to look at it, but there are some people that are half glass empty and some people have half glass full. I tend to be a half glass full kind of guy. And so the way in which we started to think about it was, but what if instead, leveraging Pareto's observation, what if instead we could actually expose more interleavings, but selectively? So that we expose only the interleavings that, yes, every interleaving is going to introduce some complexity, but at least we are going to expose only the interleavings that are going to have the potential to also pay us back in terms of performance. If we do that, then the hope is that we would be able to get most of the performance benefit that we would be able to just willy-nilly showing interleavings at a fraction of the complexity. And that is the approach that we decided to pursue, and that approach led us to a system that we called SALT. And we called it SALT because we don't take a backseat to anyone when it comes to geekness. And so, of course, if you get acid and base together, that's what you're going to get. And the idea of SALT is exactly that since no transactions are created equal, then if there are these few performance critical transactions, maybe what I should be doing is to take the transactional abstraction and massage it a little bit so that it is better suited for just the case of the performance critical transaction. For just those, I'm going to massage it a little bit. And that's the approach that we pursued. Let me tell you what I mean by massaging a little bit. So imagine that I'm taking one, I'm considering one, forgive me. I'm considering one of these performance critical transactions. And what I'm going to do is actually split this performance critical transaction in sub-components. Sub-components that I'm going to call we were on a chemistry trip here. So we call them, I know. We call them alkaline transactions. So this alkaline transaction, you can think of them as sort of mini acid transaction. And then we wrap them into something that we call a base transaction. So there are going to be, in our system, normal acid transactions, the ones that are not performance critical, the overwhelming number of the transaction, unchanged. And some transaction I'm going to call this base transaction. I'm going to recognize this structure inside them. So what is interesting about this base transaction? There are two things that are interesting about them, in my view. One is that when it comes to things like atomicity and durability, nothing has changed. These base transactions behave just like acid transactions. But where things change is when it comes to isolation. When it comes to isolation, base transactions have the ability to export a different isolation behavior to different classes of transactions. And they do that through an isolation mechanism that we call salt isolation. And salt isolation behaves a little bit like this picture. If you look at this picture, and if you look at and you tilt your head in a certain way, it looks like a duck. And if you tilt your head in a different way, it looks like a rabbit. And in a way, our salt isolation allows this base transaction to behave a little bit like this. In particular, when it comes to how base transactions interact with other base transactions or with other instances of the same base transaction, they're actually able to export to them the fact that they have internal structure and they can interleave at the boundaries between alkaline transactions. When instead a base transaction interacts with an acid transaction, it looks to it as a monolithic acid transaction. So you basically, the idea is, again, to try to expose the possibility of interleaving only when there is a benefit to be drawn from it. Okay? So if I have a base transaction interacting with another base transaction, they may actually interleave something like this, right? But if a base transaction interacts with the large majority of acid transactions, the acid transactions do not see and therefore do not have to worry about this intermediate state. They can actually, they are either going to see the state, they're either going to see the state before or the state after. So that was the idea that we had when we explored this approach. And so I'm just going to, let me just put forward that the emphasis in the talk is in giving you this journey. And there are going to be, in fact, some graphs that I'm going to show. The emphasis, admittedly, is not on a very careful analysis on the graph. I apologize for that, but there is a story that I would like, which is not a fairy tale, that I would like to tell you. And so I apologize for the fact that we're not going to spend an enormous amount of time on the graphs. But let me tell you about these graphs, at least. So the question that we asked ourselves are fundamentally a couple of questions. The first thing that we asked ourselves is, how does the performance of this salt compare with acid? And our idea was to try not just to get performance, but to get performance with limited programming effort. So how much effort was it actually necessary to achieve that performance? Another way to put it is, how many transactions did we have to basify in order to be able to get the performance that we were getting? And what we did, we actually implemented salt isolation inside MySQL cluster. We went inside MySQL cluster and opened the guts and implemented salt isolation. And here are results that we are that I'm presenting on. These are throughput latency graphs on with this particular configuration, again running on MySQL cluster. there are two applications. One is TPCC that apparently the database community uses quite liberally as a benchmark. And another application that we looked at is called Fusion Ticket, which is an online ticket reservation system that is a much larger application than TPCC. And as you can see, I mean, the numbers look promising. There is a quite significant jump in terms of throughput. One of the things that you can see here is that at the beginning, we pay some latency. The reason that we pay that latency is because if you look at what MySQL cluster does, it doesn't really provide ACID guarantees. It provides ACI guarantees. There is no real D for durability. Our system was trying to provide durability. If you did provide durability also in MySQL cluster, you wouldn't see the difference here in, the difference that you see. So the performance seemed reasonably good. How much effort was it required? For TPCC, we found that basically after we had basified 3 transactions, we were able to get to the same kind of performance virtually that you would be able to get by going full base on the entire benchmark. For Fusion Ticket, we actually saw that, you basified one transaction, we got quite a significant jump. We basified a second transaction. How do we choose the transaction that we basify? We try to see which transactions, maintaining the same load distribution, but increasing the frequency at which requests are, I think that's what we were doing at the time, which requests are submitted while maintaining the same general workload distribution, which transaction suffer a disproportionate increase in latency. And we consider those as being the bottleneck transaction, and those are the ones that we try to basify. As we were proceeding here, every time you basify a new transaction, you have to then start asking yourself about the interaction between the new states that that transaction is exposing with respect to all the other transactions that you have basified before, because now there are these new interleavings that you have to be thinking about. So as you proceed, it becomes, the work in terms of complexity increases. We didn't want to have to basify the 30-something transaction that or 50 transactions that were there. So what we decided to do was to at least get an upper bound on the maximum amount of performance that we could possibly be getting if we had gone the full 9 yards. And so basically, we actually chopped our transaction in individual operation, which of course gave up all claim to correctness. There was, of course, this execution wouldn't be correct, but at least gives us an upper bound in terms of performance. And you can see that the difference between what you would get with raw operation and just with basifying a single transaction was relatively small.
So you have 10 shards, right?
Yes.
How does it scale with the number of shards?
What do you mean by how does it scale with number of shards?
Let's look at the number of shards. So now you get 6.6.
We try to, I'm producing the result that we had for the maximum number of shards that we were able to get, because we were running on Cloud Lab, and there were only a certain number of machines that we were going to be able to get. So I wouldn't be able to tell you. Sorry? Right, probably would be comparable. Sure.
In between, you have the base, what we call the base transaction and the other transaction. If I take the base transaction and think of it as a single big transaction, between this transaction and the rest of the transaction is the usual ACID system?
The usual ACID system. Unchanged, completely unchanged.
You take a bunch of transactions and you say, here now the whole system will be the asset, and now here I'll do some play.
One way to look at it is that, yes.
What's the difference between this and what's called the mini transaction, the Aguilara?
It's different. I don't want to get in. Yeah, it's different. So when we had, oh, yes.
One more, I think we haven't told us enough to ask the really interesting questions. One of the high-level questions, can we handle aborts?
Yes, we can handle aborts.
Of the base pieces?
We can handle abort. I mean, we assume, just like in base, the base mechanism does, that you can actually roll forward.
So no,
See, yes. It's actually, let me get back to you, if you don't mind. Because this is a subtle point that we discuss in the paper, and as I stand here, I don't recall. And so I would just be blabbering, and I don't want to blabber. No, not necessarily. Not necessarily. They might, but they don't have to. It may just be that there are some conflicts that are just occurring between, for instance, one thing that we're going to see later when I talk about other experiments that I should discuss how different transactions within the TPCC workload operate.
Once we separated the snapshot transaction, it has been separated within them in a special way, something like, I don't know,
It's an.
Two other quick questions.
Yes.
So one is that there is a slight decrease in the throughput, if I see it correctly.
That's
From
there is some
Is
work.
that because you have more context switches, basically, because you have your device transaction in smaller pieces, or?
It is. I think it's because of that.
Yeah, I see.
It's minute.
And the other thing would be nice
Yes.
to understand. So here you say only.
I told you I didn't want to discuss the graphs, but sure enough.
No,
No, it's okay. It's okay.
You have one transaction, for instance, for the fusion together.
Mm-hmm.
I'm just curious about this because the other metric is the frequency, right? If I'll be curious, is that it can be also probably it is because it's a heavy transaction, but it also
Could be that because it runs often.
Yeah, in theory, I can have 100 type of 100 different transactions, but one transaction is executed 1,000 times.
Correct.
While the other is
Correct.
only one time. So
Correct. In fact, one of the things that we find is that sometimes there are conflicts that arise between multiple instances of the same transactions that are running concurrently. And we're going to get to that also. So, great. So when we started having this result, naive as we were, we felt happy. And I started going around and trying to tell people about these results. Not that we had any illusion that the thing was broken, but at least we started to feel reasonably good about ourselves. And yet what was happening while I was going around, often something like this would happen. I would discuss these results, and people would say, this is great, but what about those transactions that you have to basify? What do you do about the transaction that you have to basify? And I would say, well, there is nothing magical about that. It's complicated when you have to basify something. The problem, the good news is that before you had to potentially basify everything, now you only have to basify few, and you don't have to worry again about all the interaction between the ACID transactions and so the unmodified transaction. And they would say, well, yeah, that's great, but you know, how do you basify those transactions? It's still complicated. And so as I was you know, talking to people, I had the impression that people were trying to tell me something. There was some message that they were trying to send me, but I couldn't quite figure out what they wanted to say. But eventually it dawned on us that what people were trying to tell us is that they really like the acid paradigm. We were trying to find sort of a sweet spot between acid and base, but what people were saying is that once you go away from acid, there is no sweet spot. It's only a matter of how sour it gets, but there is really no sweet spot. And so we decided to say, you know what? Let's actually then try to embrace acid with no ifs or buts, right? We're just going to go for acid. And however, we are going to try to just make acid maybe a little more performant. And the way in which we thought about this, and this would be sort of the second step in this trajectory that I wanted to share with you, was actually to go back to the original observation, the Pareto observation, that basically not all transactions are created equal. And if not all transactions are created equal, our first answer to that observation was, our first response to that observation was that we should use a flexible abstraction. And the next obvious thing, if we want to maintain the abstraction identical, the next obvious thing that you can imagine doing is instead trying to have a flexible way to implement that abstraction. And that led us to a new system that we actually called CALLAS. We called it CALLAS both because I love opera and because it turns out that in Greece, the most common type of salt is called CALLAS. So there was a subtle message that was being sent also there. And the idea of CALLAS was that, you know, there is one, if you want, abstraction, but there are possibly multiple implementations of that abstraction, and that's what we wanted to achieve. And the starting point of our thinking was, so we want to, why do we want acid and a single abstraction? We want acid and a single abstraction because having just one thing that you program against, one thing to think about, is of course simpler than having multiple. So having a uniform abstraction can possibly lead to greater ease of programming. But if you push this desire for uniformity to implementation as well, there is a price also that can be paid for that. Because if I have a uniform implementation of that uniform abstraction, that means that I have basically an implementation that has to be such that when it comes, for instance, to conflicts, has to be able to handle any possible conflicts that you throw its way. It's sort of one of those element of clothing that are one size fits all. As an Italian, I profoundly object to say, no, I'm kidding, but it's, you know, of course, if you have to be able to address all possible kind of conflicts, chances are that there are going to be some kind of conflicts for which the mechanism is going to be very well suited, and others in which it will not be perfectly well suited. It will be okay, it will be safe, but it will not be as performant as possible. So that led us to then try to propose a different way to structure concurrency control, which we called modular concurrency control. And the idea of modular concurrency control is is basically to do something that we have been told that we should be doing since we started graduate school, at least. That is to, first of all, it's a good idea to decouple abstraction and implementation. When it comes to the abstraction, I just want to provide acid abstraction to everyone. When it comes to implementation, this is what I'm going to do. I'm actually going to, at least that was the idea that we had at the time, I'm going to partition my transactions into groups, and I'm going to associate with each group a specialized concurrency control that is going to be very well suited for just that group of transactions. The intuition is that since that concurrency control needs to only work correctly, not for every transaction, but for that set of transactions, it can be more aggressive. Then, of course, there may be conflicts that may go across groups, and I'll have to do something with conflicts that go across groups. But, you know, and the idea was that if we are, you know, yeah, and having a cross-group concurrency control. And the idea is that if we do a decent job, then we can do another things that our forefathers told us that was a good thing, which is separation of concerns, right? So we can, ideally, we should be able to think about correctness within each of the groups, and what happens in terms of me establishing correctness within each of the groups should be independent of what happens in the other groups, okay? And again, the idea is that, as I was mentioning before, by limiting the scope of what a concurrency control mechanism has to handle within one group, possibly I can be more aggressive. The third insight that came up over time is that the structure that I presented to you has a bunch of concurrency control within each group and a cross-group concurrency control mechanism. As it happens, as you become more aggressive on each of the groups, what happens is that you may end up pushing up more conflicts in the cross-group. And the cross-group itself, as we came to realize, may become a bottleneck. And so the idea, perhaps not surprisingly, is that what you should be doing is actually recursively apply modular concurrency control also to the cross-group mechanism. So intuitively, what you may think of is that at the beginning, you may imagine that you have some concurrency control that is responsible for managing the conflicts among all the transactions. But this concurrency control can actually maybe delegate responsibility for managing conflicts among different groups of transactions to some other concurrency control. And then if there are conflicts among these groups, it is actually responsible for dealing with them. And then, you know, you can imagine recursively doing something along these lines. And we built a system, a follow-up to CALLAS that actually implemented this approach. We call that system TEBALDI. For those of you who are into opera, there is no need to explain, but these are TEBALDI and CALLAS. They actually used not to like each other that much because they were competing. You know, so what I'm going to talk about is not the entire TEBALDI blah, blah, blah. Instead, what I'm going to talk about to just discuss the key idea is the simplest version, the CALLAS version, in which there was just one single concurrency control mechanism, with the understanding that there is a price that we would pay in performance if we kept it like this. So the first thing that I would have to do is to try to convince you that I have correctness under control. When it comes to correctness here, I'm going to use, with apologies to Natasha, I'm going to use the formalization. This was actually work prior than what we did with Natasha. In fact, we became so aware of the work of Adia and Liskov by doing this work. Adia and Liskov have this beautiful, beautiful piece of work where they formalize different isolation levels. They introduce a bunch of criteria for determining when correctness holds. At the core of all of them, and for simplicity, I'm going to focus simply on that, there is some requirement of no circularity in some well-defined graph, okay? And this graph tends to be what sometimes is called a direct serialization graph, where the nodes are committed transaction and edges indicate dependencies between these transactions. So in a situation like this, if I have transaction T1 and T2, and I have a dependency like this, that would show itself in the DSG in that form. And if I have another dependency in the other direction like this, then there would be a dependency in the other form. There would be a cycle. That's no good. Okay, so we don't want cycles. Okay, so then if I want to show correctness, I have to show you that there are going to be no cycles within each group, and then that there are going to be, under the assumption that there are no cycles within each group, there are not going to be cycles across groups. And I'm going to actually start from the latter. I'm going to assume that I've already argued to you that there are no cycles within each group, and I'm going to show that there are no cycles across groups. Okay, sorry, I already said that. So I'm going to show that there are no cycles across groups. And the idea that we use there is an idea that, for reasons that are whatever, we called nexus locks. Okay, so what are these nexus locks? Nexus locks are locks, but they are ubiquitous. Every time you try to touch an object, you're going to get one of these nexus locks. And that seems like a very bad thing, because remember, what I want for my cross-group, correctness cross-group, I don't want the correctness cross-group to be necessarily highly performant. For performance, I'm trying to exploit the per-group highly optimized mechanism, but I certainly don't want the cross-group to step in the way of performance. It should just give me correctness without messing things too bad in terms of performance. And if I touch, if I say that this is ubiquitous, is pretty scary. But it turns out that these nexus locks, and am I out of time? Mamma mia, as we say in my native tongue. So there is no way I'm going to be able to. It's such a beautiful story, my friends. Well, I'm just going to. Okay, I'm going to try to. Okay, so nexus locks. At least maybe I can explain to you how these nexus locks work. There is something cute in that. Nexus locks have the following property. When they are invoked by transactions that are in different groups, remember that we have these groups, right? If they are invoked by transactions that are in different groups, nexus locks work just like locks. So there is no conflicts only if both are acquiring for read, otherwise you have to block. But if they are acquired by transaction within the same group, there is no conflict, okay? And the reason is that I want to make sure that these nexus locks are not interfering with whatever performance I'm going to try to squeeze out of the in-group mechanism. So this sounds reasonable. Unfortunately, it also sounds incorrect. And here I'm calling this a subtle problem. You may also call it, depending on how you feel, a gigantic hole. Here is the subtle problem. Here is a situation in which I have a transaction that touches this variable A, acquires the nexus lock on A. There is another transaction that also wants to touch A. Since it is in the same group, there is no conflict, right? So it's going to be able to acquire the nexus lock on A. It's fine. Suppose that then and there is a dependency now that is generated between T1 and T2. Now it touches B. acquires the nexus lock on B, and then it commits and releases all the locks. And then there is a transaction after it has committed. There is a transaction outside the group that actually touches B, and that actually generates now a dependency between T2 and T3, right? And you see perhaps what I'm going to do now. What I'm going to do is to have transaction 3 actually touch C, and then commit. And after this commits, I have transaction A touch C, and now I have the terrible cycle, right? So we have a problem. So one thing that we asked ourselves is, okay, we do have a problem. How come that the normal locking mechanism doesn't have a problem? And the reason that it doesn't have a problem is that traditional locking depends on with completes before. So if transaction 1 depends on transaction 2, basically transaction 2 cannot start unless transaction 1 has completed, which would mean something like this, right? You don't have a problem in that situation because that would be the execution, and there would be no problem. In our case, that tying only applies for transactions that are in 2 different groups, right? But when I'm looking at transaction within the same group, that is no longer true, and it's no longer true for good reason, I would argue, because if I have that within a group, then bye-bye, ciao, ciao, as we would say, for all hopes to actually get performance within a group, because I'm basically executing transactions sequentially within a single group. So the idea, the way in which we ended up solving this problem was actually taking that linking between completes before and depends and refining it. Refining it by saying that it used to be that if T2 depends on T1, T2 cannot start before T1 completes. And instead, we are going to change this to if T2 depends on T1, then T2 cannot release its nexus locks until T1 releases its nexus locks. So that would mean that where in traditional locking, I would have this kind of situation in which they have to execute. Instead, I'm going to allow them to execute side by side. But once this thing commits, it can actually release all the resources that it was holding, can inform the world that it has committed, but it cannot release its nexus lock. It should keep its nexus lock until transaction 1 is executed, and that guarantees that I'm going to be okay anyway. You're not convinced.
I don't understand what's happening in group 1.
Oh, you don't understand what's happening in group 1.
Right, but there is something that is what's happening there that you're not doing.
So the correctness about what happens in group 1 is something that I haven't talked about.
Yeah, don't understand.
Exactly. So that's very true. Yeah. So all I'm saying is that
at this level, if you tell me group 1, don't worry about it, think of it as one big transaction, then this is just nested transactions or something like that.
so if I had time, I would tell you what's happening in group 1.
Okay. That's why I'm shaking my head. It's not that it's wrong or anything, I just don't know that.
Yeah, so if you recall, what I said is assume that there are no cycles within group 1. I just want to make sure that this mechanism doesn't introduce cycle across. That's all I said. And that's, I think, I showed. That's all. Okay. So now, in theory, I should tell you about isolation within each group, right? And when I tell you about isolation within each group, again, the argument is that by using this modularized approach, I can squeeze performance. And to try to convince you that that is good, that is true, I'm going to begin by arguing that, in fact, applying this modular approach can actually help squeeze performance also from techniques that have been around 25 years. So in particular, I'm talking about a really nice technique that is known as transaction chopping from Shasha of quite a while ago. And transaction chopping is kind of magical in a good way. It actually says, I take my set of transactions, I can use some static analysis, and through static analysis, I can determine the provable best way in which I can chop transactions while maintaining serializability. So I can basically get free concurrency without weakening my isolation guarantees at all. That's beautiful. And the way in which I convince myself that this works through static analysis is by doing the following. They actually take their transaction and imagine that they are connecting the operation within the transaction with something that they call S edges. And if there are conflicts between transactions, there are potential conflicts in transactions, they are connected by something that they call C edges. And you get one of these transaction chopping correct if there are no what they call SC cycles in their graph. And you can see here that if I have an SC cycle, what I can do is actually take those two pieces, put them together. I reduce concurrency, but I remove danger for my isolation guarantee. And it should be intuitive, and I would have graphs to show you, that if instead of having to guarantee no SC cycles among all transactions, I only say that I have to guarantee no SC cycle within just a group, the chances that my scheme is going to work are significantly higher, right? So modularity just is going to help just. But there are some situations in which SC cycles are kind of difficult to avoid. And we discussed before the fact that some transaction may happen time and time and time again. And if that is the case, then I may have situations in which I have self-conflicts of transactions of type A that are executing and conflicting with other transactions of type A. And in a setting like this, I can do my SC cycle analysis as much as I want, but in the end, the only thing that I can do is actually execute things like this because, right, it really doesn't help. So one thing that we introduced in our paper was actually a technique that relies on the following observation. If you look at these edges are undirected edges, right? And they're actually considering potential conflicts that may exist between tables on one transaction and tables of another transaction. But let's see actually what is happening at runtime. If you think what is happening at runtime, there is actually going to be, at some point, some specific dependencies that may end up generating between these two transactions that are executing, that is actually injecting an arrow in that undirected edge. And then what I have to do then in order to maintain correctness, all I have to do is to make sure that that arrow is going to be respected by the other conflicts. And if I do that, then I can actually execute my transaction in some kind of pipeline fashion. And actually that, furthermore, since I'm doing things at runtime, instead of considering pessimistically that there may be a conflict between two tables, I can actually verify whether there has been a conflict on a row, and only then actually enforce these controlled pipeline execution. And I can generalize all of this, and I guess I should stop, right? What is the bottom line that I would show to you? What I would show to you is that what we found was that with this approach, we were actually able to get below 10% difference between the performance that we were getting with salt and the performance that we were getting with this. The difference was that in salt, you had to basify. Here, you didn't have to basify anything. And you were basically sort of getting this, this performance, I don't want to say for free because it's never for free, but without requiring the programmer to having to restructure their application. And you were asking me what was happening at the guy at the end. So since I don't want to, this is what I was hoping would be happening to the guy at the end. You know? he goes away, he's rescued, goes away, finds happy life, and perhaps the pendulum is, at least for a little bit, out of work. All right, that's what I had to say. Sorry for running late.